Okay, so this is a video for second semester graduate algebra students on integral closures. So we're doing so let me just give the title here. Integral closures / normalization. And so the goal of this video is to define the notion of integral closure and normalization. So the goal, is I guess we have two things. So define integral closures. For an extension of rings. So this would be like the integral closure of so with respect to B of A. So this is what we'll do. So this will be a new ring. Okay, so the idea is like so e.g. so the integral closure in Q of I of Z. So this will be the Gaussian integers. Okay, so this is an example. The other thing that we're going to do is we're going to show that show integrally closedness so something is maybe we can call this normality. So normality and integral closedness are the same thing. This is a local property. Okay, so which means that so something is a local property is, if you recall, that yeah, if property P holds, then property P holds property P holds if and only if it holds for the localization at every prime ideal. So okay, so like A is integrally closed in its field of fractions if and only if AP is integrally closed in its field of fractions, where AP is the localization of A at a prime ideal P. All right, so this is what we're going to be talking about, and so let me give a definition. So let's say so given this extension of rings, we say B and B is integral over A if and only if there exists some monic irreducible polynomial, let's see, in A of X. So this is well, it doesn't have to be irreducible. It's some monic polynomial, right? So that means that its top degree coefficient is 1. If some monic such that G of B is equal to 0. Okay, so this is what it means to be integral. So so back to this example that we were doing. So for example, here this Z adjoin I. So if B is equal to I, and this is an element of Z adjoin I. Okay, so this is B. And then we have A, this is Z, right? Then here we see that G of X is equal to X squared plus 1 works. So this is monic because the top degree coefficient is 1. So you notice that G of I, this is I squared plus 1, which is minus 1 plus 1, which is 0. Okay, so that's what that's the standard example. Okay. So let's say that maybe we can give a definition of integrally closed now. Let me just do that real quick. So let A be a domain. All right. Okay. Oh, I don't need to underline that. So let A be a domain. So we say A is integrally closed if and only if, for all, let's say, B in kappa of A, so this is the field of fractions of A, so this is the residue field of the generic point of A. So for all B in kappa of A, if B is integral, then B is an element of A. Okay, so I'm going to show some examples of integrally closed ring extensions. So I'm just going to give you the most basic examples. Okay, so the basic example is when A is equal to Z, and it's a subset of Q, and this thing is B. Okay, and so suppose. Okay, we're essentially going to show that this thing's integrally closed. So we're going to show that the integral closure in Q of Z is just Z. So it's already the set of integral elements. So suppose that R over S, this is B, in Q is integral. So this means that we have some integral polynomial, right? That so there exists some g of x, which we'll say is a0 plus a1x plus dot 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 plus x to the n. This is a monic polynomial with coefficients in z, such that g of r over s is equal to 0. Okay, well, this thing here, this is the same thing as saying that, so we'll start with the leading coefficient, r to the n, and then we'll multiply through by s to the n. So this will be a1, so an minus 1. So I'm reading this backwards now. R to the n, so let's do s, r to the n minus 1, plus a to the n minus 2, s squared, r to the n minus 2, plus dot 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 dot, plus a0, and we have s to the n is equal to 0. Okay? So this element is integral if and only if this is 0, and so this implies that r is integral. Oh, okay. So, well, I mean, this is true, but this is not actually what we want to do. So this is a trick that you'll use later. So we're not going to do that. So this implies that if and only if, so that r to the n is equal to, okay, now we can bring this to the other side, an minus 1, r to the n minus 1, plus an minus 2, s, r to the n minus 2, plus blah, 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 a0, sn minus 1 here, s, okay? So this means that s divides r to the n minus 1, so s divides r to the n, so this implies that s is equal to plus or minus 1. So we could have taken them to be co-prime to begin with, so this means s is equal to plus or minus 1, and so so that r over s is an element of z, so it's an integer. Okay, so so we use this relation to get this, and so this shows that every rational, so if a rational number is integral over the integers, it's an integer itself. Okay, I should say the same thing, same proof shows that for say works for A, UFD, and B, the fraction field of A. Okay, so in particular, a UFD is closed is integrally closed in its field of fractions. Okay, I'm going to interrupt the video because I think the presentation will be a little bit better if I talk about faithful modules first. So I'm going to do that right now. So faithful modules. Okay, so so these are things where so the idea is let me just give the definition. So definition. So M in mod R is faithful if and only if the annihilator of M with R is 0. Okay, so multiplication by R is injective. So by R and R is injective. So it's torsion free. Okay. So that's the idea. So let me make a quick remark here, so that if if rho from G to automorphisms of a vector space is a representation, right? So then V has the structure of, so anytime you have a representation, you can make a left ZG module of a left ZG module. So ZG modules and representations are the same, right? Via, let's say, G times M. So this is an element of the group ring. Define how a general element of the group ring acts. You just need to define how one element goes. And so this is defined to be rho G of M. And so rho G is the image of G in the automorphisms of V. So this is for M, an element of V. Okay? So so it has the structure of a left ZG module via this thing. And so in this terminology, so this map is injective conversion. Okay, so rho is faithful, the representation is faithful, if and only if V is a faithful ZG module. Okay, so we're mostly doing things over commutative rings. This is the one example where we care about non-commutative things. So this is one of the examples. And so this is where maybe the terminology comes from. Okay, so so now let's prove the following thing. So let's do like a little lemma here about faithful modules. So fix M, which is an R module, mod R. Okay, so R is a ring. So the following are equivalent. Okay, so the following are equivalent conditions for faithfulness, right? The first one says that if M is a non-zero element, then if AM is equal to BM, this implies A is equal to B. Okay, so for okay, so this is for A and B in so I guess you can say for all A, B, an element of R, this ring R. Okay, so okay, so that's the first thing. The second thing says that for all A, B in R, if A is not equal to B, this implies that there exists some M in M with AM not equal to BM. Okay? The third thing says the following. It says that for all elements of R, if A is not equal to 0, then so if a is not equal to 0, so then there exists some m where am is not equal to 0. Okay, the fourth thing is that the annihilator of r of m is equal to 0. Okay, so here's this lemma, and let's do the proof here. Okay, proof. Okay, so 1 implies 2. Okay, so so if 1 implies, okay, so suppose not. So if a is not equal to b, and am is equal to bm, then well, then we have a minus bm is equal to 0. Well, let's see. Okay, if for all m, so we'll do this and not this. Okay, for all m, am is equal to bm, then well, I mean, this is directly the negation. So let me just say, this we actually don't even need to do this part, right? That's, I guess, for the third part, right? So then this directly contradicts, right? This contradicts. It's almost tautological. Okay. Let's do 2 implies 3. Okay, so 1 if and only if 2 is pretty... Okay, so let's just do this. These are exactly the same. Okay. Yeah, they're the same. Okay, so let's suppose... so let's look at 3. So 2 implies 3. So if... okay, so if there exists an element of m such that am is not equal to 0, so if okay, so let's take, so for 2 implies 3, take a to be take b to be equal to 0. Right, that's all you need to do. So here, if b is equal to 0, you get the exact same thing. Okay? And so the third statement, so 3 implies 4. What is this statement? So this is just saying that the annihilator is not equal to 0. So let's see. So if the annihilator was if the annihilator was not equal to 0, so that means there would exist some thing here such that for all m we would be equal to 0. So this is also pretty clear. So this is clear. Because otherwise there would exist some a in the annihilator of r of m, which would contradict contradict 3. Okay, and so so 4 implies 1. Let's do that one. Okay, so 4 implies 1 is the following. So okay, so what do we need to do? So suppose that we had so suppose that we had some a and b. So suppose we had some a and b here, right? Which were not equal to each other. So if suppose. Okay, so then if, let's just do this. If am is equal to bm, so then, well, clearly a minus bm is equal to 0. Okay, and hence a minus b is in the annihilator. So this is a statement for all m, right? So this is in the annihilator R of m, but this is 0. So this implies that a is equal to b. All right. So that concludes the proof of this part about the this faithfulness. Okay. I mean, this is pretty simple. I should have just let you do this on your own. Okay, so all the integral elements are already contained in A. Okay, so to start this off, the study of integral elements, we're gonna do this thing where we do a bunch of equivalent things. Okay, so let's do a theorem. Okay, so the following are equivalent for an extension here with B and B. Okay, one, the first thing is that B is integral over A. So it satisfies some monic irreducible polynomial. So the other thing is that A adjoint B, so this is a new ring, is a finitely generated A module. So for example, if we were going to join an indeterminate X, this wouldn't be true. Okay, the third thing is that so there exists some C, a finitely generated A module, such that A adjoint B is contained in C. Okay, the fourth thing, so there exists some module, so this is a faithful so some faithful A of B module. So that means the annihilator is 0, which is finitely generated. As an A module. Okay, so faithful again means that there's no annihilators. Okay, I mean the only annihilator is 0. That's what it really means. Okay, so all right. So this is what we have here. So I have a little thing about faithful modules, but let's see. I have okay. So let's see if we can prove this. So let's do the proof. Okay. So the proof of so B is integral over A. So so this one is true. So here, so 1 implies 2. Since, okay, so why is this true? So this is because, so we have A adjoint B, so this looks like, A plus AB plus AB squared plus dot 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 plus AB to the n minus 1. Okay, let's suppose that it satisfies a polynomial of degree n, so GB, so this is equal to 0, this is equal to A0 plus A1B plus dot 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 plus AN B to the n. Okay, and actually, this term here is 1, right, because it's monic. So that means that, okay, this thing can keep going. Okay, we'll do A B to the n. But these higher order terms, these wrap around, right? So this thing wraps around using the relation, so using this relation that B to the n is equal to minus A0 minus A1B minus dot 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 minus an minus 1 b to the n minus 1. So this thing allows us to write this, show that it's finitely generated, plus a b squared plus dot 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 plus a b to the n minus 1. Okay, so this shows finite generation. Okay, so clearly 2 implies 3. So 2 implies 3. So let's C be A adjoin B. It's finitely generated. Okay, so to verify this condition, right? So for faithfulness, so this is supposed to be m is equal to ab. But let's just do this one. So so we need to show that there exists some. So I'm going to use one of the conditions previously. So one of the conditions is that so that it doesn't annihilate something, right? So there exists some m in M. Let's put it this way. So for all A in A adjoin, let's do this, so let's say for all Y in A adjoin B, so there exists, so this is for Y not equal to 0, so there exists some M in M with AM or YM not equal to 0. Okay, so this is the same thing as saying the annihilator is 0. And so here what do we do is that since A adjoin B is contained in C, this is contained in C, which is equal to M. So this thing contains 1, and we'll take this to be equal to M. And we know it's not equal to 0 because Y times M, so this is Y times 1, which is just Y, which by definition is not equal to 0. Okay, that gives us that part. Okay, so this is a video for second semester graduate algebra students on integral closures. So we're doing so let me just give the title here. Integral closures / normalization. And so the goal of this video is to define the notion of integral closure and normalization. So the goal, is I guess we have two things. So define integral closures. For an extension of rings. So this would be like the integral closure of so with respect to B of A. So this is what we'll do. So this will be a new ring. Okay, so the idea is like so e.g. so the integral closure in Q of I of Z, so this will be the Gaussian integers. Okay, so this is an example. The other thing that we're going to do is we're going to show that show integrally closedness so something is maybe we can call this normality. So normality and integral closedness are the same thing. This is a local property. Okay, so which means that so something is a local property is, if you recall that yeah, if property P holds, then property P holds property P holds if and only if it holds for the localization at every prime ideal. So okay, so like A is integrally closed in its field of fractions if and only if AP is integrally closed in its field of fractions, where AP is the localization of A at a prime ideal P. All right, so this is what we're going to be talking about, and so let me give a definition. So let's say given this extension of rings, we say B in B is integral over A if and only if there exists some monic irreducible polynomial, let's see, in A of x. So this is, well, it doesn't have to be irreducible. It's some monic polynomial, right? So that means that its top degree coefficient is 1. If some monic such that g of b is equal to 0. Okay, so this is what it means to be integral. So, so back to this example that we were doing. So, for example, here, this z adjoin I. So b is equal to I, and this is an element of z adjoin I. Okay, so this is b, and then we have a. This is z, right? Then here we see that g of x is equal to x squared plus 1 works. So this is monic because the top degree coefficient is 1. So you notice that g of I, this is I squared plus 1, which is minus 1 plus 1, which is 0. Okay, so that's what that's the standard example. Okay, so let's say that maybe we can give a definition of integrally closed now. Let me just do that real quick. So let A be a domain. All right. Okay. Oh, I don't need to underline that. So let A be a domain. So we say A is integrally closed if and only if for all, let's say, B in kappa of A. So this is the field of fractions of A. So this is the residue field of the generic point of A. So for all B in kappa of A, if B is integral, then B is an element of A. Okay, so all the integral elements are already contained in A. Okay, so to start this off, the study of integral elements, we're gonna do this thing where we do a bunch of equivalent things. Okay, so let's do a theorem. Okay, so the following are equivalent for an extension here. With B and B. Okay, the first thing is that B is integral over A. So it satisfies some monic irreducible polynomial. So the other thing is that A adjoin B, so this is a new ring, is a finitely generated A module. So, for example, if we were going to join an indeterminate x, this wouldn't be true. Okay, the third thing is that so there exists some C, a finitely generated A module, such that A adjoin B is contained in C. Okay, the fourth thing, so there exists some module, so this is a faithful so some faithful A of B module. So that means the annihilator is 0, which is finitely generated. As an A module. Okay, so faithful again means that there's no annihilators. Okay, I mean, the only annihilator is 0. That's what it really means. Okay, so all right. So this is what we have here. So I have a little thing about faithful modules, but let's see. I have okay. So let's see if we can prove this. So let's do the proof. Okay, so the proof of so B is integral over A. So so this one is true. So here, so 1 implies 2. Since okay, so why is this true? So this is because so we have A adjoin B. So this looks like A plus AB plus AB squared plus dot 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 plus AB to the n minus 1. Okay, let's suppose that it satisfies a polynomial of degree n. So GB, so this is equal to 0. This is equal to A0 plus A1B plus dot 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 plus AN B to the n. Okay, and actually, this term here is 1, right, because it's monic. So that means that, okay, this thing can keep going. Okay, we'll do A, B to the n. But these higher order terms, these wrap around, right? So this thing wraps around using the relation. So using this relation that B to the n is equal to minus A0 minus A1B minus dot 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 minus AN minus 1 B to the n minus 1. So this thing allows us to write this, show that it's finitely generated, plus A B squared plus dot 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 plus A B to the n minus 1. Okay, so this shows finite generation. Okay, so clearly 2 implies 3. So 2 implies 3. So let's see B A adjoin B. It's finitely generated. All right. Okay. So okay. There's a faithful AB module which is finitely generated as an A module. So I think you just mod out. Let's see. AB is contained in C. Okay, so we'll take C to be this. So let's see. Faithful AB module. So I think that for 3 implies 4. So so we use that C is equal to M. Or let's see, I think C is equal to AB. Okay, so let's come back to that in a second. All right, and so the hard part of the theorem is 4 implies 1. Okay, and this part uses the Cayley-Hamilton theorem. So this uses okay. So let's do this. So okay, so here's what we're going to apply it to. So suppose So suppose M is a faithful, let's say faithful A adjoint B module. Okay, let's do this. And so let phi from M to M be the map where we take phi of some little m and we do B M. Okay, so by faithfulness, so phi of so phi of M, so this is BM, which is contained in M. Okay, so so this is BM. It's contained in M. So this means, so by Cayley-Hamilton, so there exists some polynomial P of t in A of t such that, which is monic, because it's a characteristic polynomial. It's like a characteristic polynomial of the endomorphism when you put it in coordinates, right? Monic with P of B is equal to, or sorry, with P of, well, yeah, so since this is multiplication by B, so it's P of B is equal to 0. All right, and so what were we trying to show? So we were trying to show that B is integral over A, okay? And that precisely shows that here that this is the polynomial that witnesses integrality. Okay? Okay. Okay, so I'm going to continue with some lemmas about integrality. Okay, so fix, so lemma. So fix A contained in B rings. Okay, and so in let, okay, so now I'm gonna make two statements. Okay, and this is kind of a cool thing. Okay, the first thing says is that if S is a subset of the set of integral elements, which is finite, so B integral over A, so this is finite, and the cardinality of S is less than infinity, then here A adjoint, so the AS is a finitely generated A module. Okay, so we can get this thing to be a finitely generated A module. So the second thing that I want to say is that so int BA, so this is the set of B in B such that B is integral over A. So this thing is a subring. Okay, so there's these two things. This is really cool. So that we have the set of integral elements is not necessary. You don't necessarily think it's going to be a subring, but it is. Okay, so let me do a proof here. Okay, so one. Okay, so one I'm going to leave as an exercise. The hint is to use the four criteria. Okay, so let's do the proof of the second part. Okay, and so so let's let alpha, beta, and B be integral elements. So by the previous number, okay, we can take the module or the ring spanned by those things. So this is a finitely generated A module. Okay, so by the third characterization. Okay, so let's say by the 3. So this is 3 of here. So so they're contained in a finitely generated A module. I mean, I guess. Oh yeah. This is what we want. Where am I? Okay, let's see. So so this is a finitely generated A module. So okay, so by 3, so A, since let's do this, A of A plus B, and A of A times B. So these are contained in A, alpha, beta. So this is C. Okay. Both of them must be integral. Both A alpha plus beta and alpha times beta must be integral. Okay. All right, and that's all I have to say about that. All right. Okay, so all right, great. Now we've shown that that this thing. So the point, right, is that this integral closure is a ring. Okay, and so there's a special case that we'll consider. So there's a special notation. So if B is the fraction field of A, and let's say A is a domain, this isn't necessarily all you need. I actually have a video on this, but you just need A to be reduced, right? So if this is true, then we use the notation O of kappa of A. So this is defined to be the integral closure of in kappa A of A. Okay, so this is a special notation that we'll use. So this O notation. Okay. All right. So let me just give some transfer results now. Okay, so I'm going to state some transfer results now about integral closures. So here's some transfer results. So here, so if we have 3 rings, A is contained in B is contained in C, and this one is integral, and this one's integral, that implies the composition is integral. Okay, and so the idea, so these are going to be exercises. So the idea here is to use the module property. Okay. So the module finite generated this as a criterion. Okay, so next, so the next thing is that integral closure is a closure operation. So it says that, so what does it say? So it says that the integral closure of B and A, this is the same thing as the integral closure of the integral closure here. So we don't get anything extra by considering coefficients which are integral. Okay. The third property is about quotients. Okay, and it says that if A is in B, and then P in Q, so P is a prime of A, and Q is a prime of B, is such that Q intersect A is equal to B. So this is saying that Q is above of P, or P is below Q. Okay, so if we have this situation and this thing is integral, right? So then this implies that if we were to take the quotient here, and we look at the quotient map, or we look at this as a subring, so this is an integral map. Okay. Finally, we have the property about localization. Okay, so this is about localization, and it says that if you localize an integral extension, then it'll be integral. So if S is contained in A, it's a multiplicatively closed set, so it contains 1. And if A contained in B, if this is integral, so this implies that that the localization of A, this business here, is integral. Okay, so that's what we have here. So okay, so the proof here is an exercise. So I'm going to do the proof of this one here. Okay, so let's do the proof of 2. Or actually, let's do 1. Okay, so the proof of 1 says that so we want to show that every element in C is integral over A. Okay, so C and C. So take this. Okay, and so we know B of C is a finite B module. But we can even do better, right? But we could do better. Okay, and so let's just look and see what happens. So we actually have B1 plus C, so this B squared C squared plus dot 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 plus A to the n, or sorry, B to the n minus 1, C C to the n minus 1 plus C to the n is equal to 0. Okay, so how can we do better? Well, we know B prime of C is a finite B prime module. Okay, so where B prime is B prime is this thing where we take A and we adjoin all of the coefficients. Okay, so this means this is what we have. All right. The other thing that we have is that B prime is a finite A module. Okay, and so And so this means that b prime of c will be a finite A module. And this contains, which contains A of C, and hence proves C is integral. So we're using the criteria that we had before. So this criteria about let's see, integrality here. So we're definitely using this one here, the number 1 there, and then we're using this one here. So this one, and so like 3 and 4. I guess we're just using 3 actually. Okay. Okay. So what else do I want to do? What else did I want to do? So I wanted to give another proof. So something that you can use for the other thing. So this is a very useful statement here. So the statement that I want to prove is the following. So theorem or lemma. And maybe you can use this for the other one if you want. But this is kind of the yoga of kind of how these things go. Maybe this gives away too much from some of the exercises that I was saying, but okay, so let S be a subset of A here, be multiplicatively closed. Okay, the star doesn't mean units, it means monoid. Okay, and then let A be a subring of B. Okay, so then the integral closure of B and A. So this is going to be, so if I take the localization of this, this is the same thing as the localization, the integral closures of the localizations. Okay, so this is what we'll want to prove. Okay, so let's do, okay, so we'll have to do a claim, and then we'll have to do a proof. So, okay, so let's do let me just do the proof. Okay, and so one of the directions is rather straightforward. So the straightforward direction, I think, is that this is contained in here. So if, let's see, so if, let's say, so let's say B over S is an element of S inverse the integral closure of A and B, okay? Then there exists some G of T monic, so AI T to the I is equal to 0 up to N, in A of T monic with the following property, let's say with G of B is equal to 0. Okay, and then let's just write this down, and then we'll like fiddle with it, and it'll pop out that this is that B over S will be integral. So let's just do it. So then we have A0 plus A. Oh, maybe I should use the summation notation. Let's use the summation notation. Okay, so we have this thing, sum of I 0 up to N of AI B to the I. This is equal to 0. Okay, so now what can we do? So we could just put in S. I is equal to 0 up to N, so AI. Okay, and then if we were going to divide by S here, B over S to the I, then we would have to multiply by S to the I here. Okay, and then this isn't monic anymore, so then then what happens is, so then we divide by the leading coefficient, so this is 1, so I is equal to 0 up to N, so we have AI, S to the I, divided by S to the N, and then we have b over s to the I is equal to 0. Okay, and this proves, okay, so now these now it's monic, but we had to we were at the cost of dividing by these coefficients. So this proves that b over s is in the integral closure of s inverse b, s inverse a. Okay, so that shows one containment. It shows that this is contained in this. Okay, so this is one direction. Okay, so the next step is to show the other containment. So we need to show that if b over t is in this integral closure of s inverse b and s inverse a, then b over t is an element of S inverse the integral closure of A and B. Okay, so it's the localization of the integral closure. Okay, and so to do this, we'll do a claim. The first part of the claim says that if B over T is in the integral closure of S inverse B, S inverse A, then B is in the integral closure like this. All right. The second. So what we're going to do is that if it satisfies a polynomial with coefficients in S inverse B, then we can just clear the denominators and do that. So this one's actually pretty straightforward. So what you'll do is you'll just multiply through by t to the n, right? Then it becomes not monic. Then you divide by. So let's see. You pull out these coefficients, sorry, of the in the polynomial, and then you divide. Then you okay, we'll do it in a second. Okay, so if int S inverse B, S inverse A. So if this is this, then B is an integral element. Okay, so the proof of one. Okay, so since b over t is in here, we have some polynomial like this. I is equal to 0 up to n. And now that it has coefficients in this thing, so ai over si. And then we do b divided by t to the I. All right, so this is equal to 0. That's the polynomial that we have. Okay, so next step is to show that. Okay, so now what do? We want to show that b is integral over S inverse A. So here's what we can do. This thing here is the same thing as the sum from I is equal to 0 up to n, ai over si. We just pull out 1 over t to the I. B, and then okay, so we have this b to the I. Okay, and then we want to make this monic, so let's just multiply by the nth coefficient. So then, so this is equal to 0. So then just multiply by. Multiply by this thing. So we'll do ai over an over sn 1 over t to the n inverse. Okay, so that's what we'll do that, and then we multiply both sides by that. This becomes a monic polynomial with coefficients in S inverse b. Okay, so b is in B. Okay, so let's do the proof of 2 now. So the only reason I broke it up into 2 steps is because these coefficients are nasty, and I just don't want to rewrite them again. So, okay, so we have I is equal to 0 up to n of ai over s to the I, b to the I is equal to 0. So this is an over s to the n is equal to 1. Okay, so this is what it means for b to be in there. Okay, so now, so I think what we'll do is we let s be s0, s1, all the way up to sn minus 1. Okay, so, all right, so then, so then I think we just introduce this term, and so let's introduce this, so let's do this, so that we have the sum. Okay, so now we'll multiply both sides by this to the nth power, okay? So multiply both sides. Let's call this star by s to the n. This gives the following. The sum of I is equal to 0 up to n. So this is still 0. So this is ai over s to the I. And then we have s to the n bi. And now we just absorb up to n ai over s to the I. Okay, now we have s to the n minus I b, so we have sb to the I. Okay, and here, so this is monic now, all right? And now the coefficients here, since s over s, this is an element of a, right? Si, right? So since these are elements of A, this is the coefficients are in A. Okay, and this is also monic, right? Okay, so this tells us SB is an element of the integral closure of A and B. So this is an element of B. And so this, and then this is the same thing as telling us that B is an element of S inverse, the integral closure of BA. Okay, and that proves the result. Okay, so we took an element which was in here, and then we showed that it was in here, right? So we took an element that, sorry, this is S inverse of A. Okay, that's what I wanted to show. Okay, and then these two things together allow us to get the conclusion. So we started with something that was it was in the integral closure of the localization, and then we get something that's in the localization of the integral closure. All right. So I guess yeah, B is in there. So then I guess B over T. So okay, so. Let's see what we have here. So this is in there, so then B is in there. That's true. And then of course that, you know, after we do that, then we get B over T is also in S inverse, the integral closure of BA. Right? So so yeah, so that this chaining these two things together allows us to conclude the second half of this. Yeah. So yeah, again, so let's look at this again. So we took something in here, we showed it was in here, right? And then we took something in here. We started with something in here. Right, then we showed it was here. Okay, so we showed it was in this part. We did a polynomial with these coefficients for B, and then we could conclude that B was in here by showing that SB was actually an integral element. Once we have that, so since B was in here, then we can just divide by T to get it in there to get the full thing. All right, that's good. So I want to give a second application. So let's just do a quick second application. So lemma. So if A is contained in B, and S inverse of, or S is a subset of A star is a multiplicably closed set. Okay, so then if this extension is integral, this implies that the extension here is integral. Okay, so let's do the proof. Okay, and so note that A over B being integral, this is the same thing as saying that B is equal to the integral closure of A and B. Okay, so that's what it means. Every element of B is integral over A. Okay, so we'll use this. Okay, so all right. So we need to show that so S inverse B. So we need to show that S inverse, so the integral, let's do it like this. S inverse B is equal to the integral closure of in S inverse B of S inverse A. Okay? Okay, but all right, this is what we need to show. That's one thing, this is the other thing. And so let's just start. So S inverse B, right? So this is equal to S inverse, so by the integral closure hypothesis, right? Integral closure of B and A. So this is saying that this is integrally closed. All right? And now, so this is the lemma. So this is the integral, this is B integrally closed. Or let's say in A. Okay. So now this is about the localization of integral closures. All right. And so this says that this is equal to the integral closure of the localization of B, or sorry, the integral closure of the localization of A over, so the integral closure of the localization of A in the localization of B. Okay. And and then you look and you're like, oh, that is the same thing as that, and we're done. Okay, so that's it. So that's a nice way of showing things are integral. So that's kind of like the easy direction of showing that being integrally closed in your field of fractions is a local property. So we'll check that. So given a domain, we'll check that the localization at every prime ideal will be integrally closed in its field of fractions. And the field of fractions of the localization is the same thing as the field of fractions of the total ring, right? And that will be enough to conclude the result. Okay, so that's that. Before doing that, I'm going to do the going up theorem. Okay, so I want to show now, I want to do kind of an application of what we just did. So let's do a lemma. Okay, so the integral closure, so what's our lemma going to say? So the lemma is going to say is that so if A is a domain, then what do we have? So we have the integral closure in the fraction field of A, of the localization of A, and so S is a multiplicably closed subset of A, okay? This is equal to the localization of the integral closure A, okay? So that's what I want to show. Proof. So we can either do that same thing we did before, so where you start to like chase these monic polynomials around, or we could just apply the previous result, right? And that's what we'll do, right? So we'll show that. So we'll show the following. We'll show that. So this is the shortest way I know how to do this. So S inverse integral closure here. Okay, so that is the same thing. We proved that this was this A, but this thing's already localized to the teeth, right? And this thing is just the integral closure in the field of fractions of S inverse of A. Right? That's the proof. Okay. Quick